Hello, everybody. I am Ehab ElSalamouny. I am a research engineer at Inria in France. And I'm going to present to you this paper, which is a joint work with Catuscia Palamidessi. I will start with describing the local privacy model, which is the main problem we consider in this work. Then I will describe a method that has been widely used in the literature to solve this problem. It's called matrix inversion method. And then I will describe a more sophisticated method called iterative Bayesian update. And I will show you some issues we found in this method, which take us to our contributed algorithm, which we call generalized IBU. I will show you some experimental results and then finish with the conclusions. In the local privacy model, we have many users. Each one has some private information or a secret, which may be his age, location, salary, and so on. We suppose that these secrets of the users follow some probability distribution theta, which is typically unknown. And the main objective in this work is to estimate this original distribution theta from available observations without violating the privacy of the users. And to do that, each user applies a privacy mechanism to his secret to produce an observation Z. And this application of the privacy mechanism is local, which means that it is done on the mobile device of the user. Now we have noisy data consisting of all observations coming from all the users. These noisy data are sent to the data collector, who is interested in estimating the original distribution theta. And the quality of this estimation is measured, of course, by the distance between the original distribution and the estimate theta hat. The main question that we ask here is which method should be used to do this job? The matrix inversion method has been used widely in the literature to solve this problem. And it works under the assumption that all users apply the same mechanism A to their secrets. And it uses the empirical distribution, which is computed from the frequencies of observables seen in the noisy data. And this empirical distribution is Q. Now the estimate theta hat is obtained by multiplying Q with the inverse matrix of the mechanism. This gives us a vector which may contain negative components. So theta hat must be transformed to a valid probability distribution by post-processing. There are two methods to do this thing. One of them is projecting theta hat to the probability simplex. And the other method is truncating negative components to zero and then normalizing the entire vector to a valid probability distribution. With respect to the performance, we find that this method is good for the randomized response mechanism and also for RAPPOR, which is based on the idea of randomized response. However, it turns to be very bad with respect to other mechanisms like Laplace, geometric, and exponential mechanisms. And these mechanisms are known to satisfy geo-indistinguishability. And to see this bad performance, let's consider an alphabet of secrets consisting of numbers from 0 to 99, and suppose that the original distributions are as shown here by these purple curves. Suppose that the users apply the linear geometric mechanism to sanitize their secrets, and then we obtain the noisy distribution or the empirical distribution shown here in the yellow curves. Suppose now that the data collector applies the matrix inversion with projection to obtain an estimate of the original distribution. And as we see here from the green plot, the resulting estimate is far away from the original distribution. This is why we consider the other method, IBU. And this is an old method introduced by Agrawal in 2001. It works under the assumption that all users apply the same mechanism E, And again, it uses the empirical distribution from the noisy data, but it is iterative. It starts with an initial distribution theta 0, and then iteratively it improves this distribution until the method converges to some distribution in the end. And the main objective of this method is that the resulting distribution is the maximum likelihood estimate, defined as the probability distribution, maximizing the probability of the observations. However, we found false claims in the original paper of EBU. One of them is that the MLE is always unique, and we show counterexamples showing that MLEs actually can be infinite in the probability space. Another claim is that the result of EBU approximates the original distribution when we have large amount of observations. And this again is not true. It holds only when the MLE is unique, and this depends on the underlying mechanism. A third claim is that the MLE is stationary, and this is not true also in many cases. Why are we interested in these claims and correcting them? Because the original paper of EBU used them to justify that the method returns the MLE. And once we find that these claims are not true, then we need to prove this property again for EBU. This is exactly what we do in our work. We introduce a variant of EBU, we call it GIBU, and we do a new analysis which leads to an important theorem showing that GIBU returns an MLE. Moreover, our method is more general because it allows each user to choose his privacy mechanism, which may be different from other mechanisms used by other users. And moreover, the same user can apply a sequence of mechanisms to his secret. And this, of course, gives more observations, which should improve the estimation process. To see the performance of GIBU, let's consider the same experiment I showed you before, but this time we do the estimation using GIBU. And from these plots, we can see that estimation performance of GIBU, in this case, is much better than the performance of matrix inversion. We also run experiments on other mechanisms like planar geometric mechanism, planar Laplace, planar exponential, and again, we show that there is a big difference in performance between our GIBU and the matrix inversion method. However, with respect to the randomized response mechanism and RAPPOR, we find that the two methods are almost similar with respect to the estimation performance. So finally, for conclusions, we found some flaws in the theory of EBU, and we correct these flaws in our analysis. We give a more general estimator, GIBU, which allows for the flexibility that I described to you before. We prove that GIBU returns correctly the MLE, and we also give sufficient conditions that this MLE is unique. And finally, we show by experiments that GIBU outperforms the matrix inversion method with respect to many mechanisms. That's it. Thank you very much.